Alright guys, so tell me if you can hear me. Let me try. Alright, so let's see. If we wind up being able to hear me okay. Alright, so regardless if you can hear me or not, or if you guys are joining us in, or if you're going to be joining us later, we will just go ahead and go from here, I think. Alright, so how far we got in the actual notebook here was we had made our model and we had done a stage 1, which is we had a frozen model. So part of our layers, so let me try and explain the layer groups again. So layer groups involves having some of the layers be frozen, and frozen means that we don't adjust them when we're training. And as a result, they don't actually learn anything. The unfrozen layers, so this would be the last layer in our model, does learn something though. And as a result, we can modify its values and help it fit our model a little bit better. So with this first model, on this ResNet 34, it was the last linear layer that had the output of all of our classes. So when we went and looked at our results, we create this classification interpretation object. And this allows us to examine on a classification problem how the model generally did on the data set. And it has a few different attributes to it. So the first is this top losses. And top losses will return the loss values along with the IDs for the losses in our validation set. So this specifically will run on the validation set only. From here, we can go a little bit more in depth. So the first is plot top losses, or the next one is plot top losses. And we pass in our number of images we want to use along with a figure size. And it will output this confusion matrix that we saw in the second half of the lesson earlier. And so it'll tell us what we thought it was, what the class actually was, its loss, and its probability that it fit that particular class. Now, what we're actually looking for in here is, does the model reasonably get some images wrong? And so, for instance, we have this Berman and Ragdoll here. So let's look at the image of a Berman cat. Let's look at a Ragdoll cat. And if we look at them side by side, off the bat, I can't tell you what's different between the two of them. And I'm sure neither can you unless you're a cat expert. And so what does that mean? that means that for our model, this Berman ragdoll doesn't actually, it's not necessarily bad that the model got this wrong. And so when you're looking at this, keep that in mind. And if it doesn't seem like something the human eye could easily figure out, then maybe there's some justification to why we got it wrong. Maybe it's a more fine-tuned and fine-grained classification problem. And there's different architectures that work a bit better for those type of situations. Now, the next one is the confusion matrix. And we saw this a little bit beforehand. The confusion matrix tells us class by class where we got wrong. So we can pass in a figure size along with a DPI, and that is how, basically how fine-grained it is. So think of it like pixels per inch. And so we can see that Abyssinian, the most I got confused with was a bangle, and the bangle with the Abyssinian again. And so you can use this to sort of figure out what classes is your model weakest to and figure out why. To a certain extent, to see if it's reasonable enough that it would make sense for our models to get this wrong. And the last thing we can do is grab a raw version of this confusion matrix. And we can use this through what's called most confused. And so we pass in a minimum value that we want, so some sort of threshold. And for our case, since we notice that most everything is between 1 and 2, we're going to set our minimum threshold for getting it wrong to 3. And this will get us most wrong class items that we were working with. And so we can see that we have Ragdoll and Berman got confused 7 times, the Egyptian Mao and the Bengal 3 times, and the Maine Coon and the Ragdoll again for 3 times as well. And this can be used for any classification problem and can help you discern and explain or help you to figure out why your model is starting to behave the way it is and figure out if it's really a good model or not and if you need to train some more. So now that we have this model that works, decently well, we've got it down to about 6%, let's try fine-tuning that. Now we fine-tune by first loading in those weights that we saved and unfreeze. So we're going to want to unfreeze all of those layers that we froze. Now we're not going to try and do a learning rate finder here yet. I first want to just show you guys what rawly will happen. And so we're going to fit for 4 cycles and not pick a learning rate. We can see that our error rate increased. This tends to happen sometimes whenever you unfreeze your weights. You might lose a little bit of accuracy, and that's due to the rest of your weights basically catching up to where they want to go to. And we dropped a little bit of accuracy there. We went from about 6 to 11. Let's see how different finding a learning rate is. Now, someone on the forum had specifically asked about how we discern rough learning rate plots. So we'll look at one here. So we'll load our original weights back in. So this is ignored. It's retcon basically. And we'll try and find the learning rate again. Now I'm going to zoom in here so we can take a look at this learning rate graph, because you don't necessarily know what to do here because it's a very bumpy, wavy curve. Generally what I wind up looking for is, okay, so where am I decreasing to? So I start decreasing from about 1e-7, and 1e-6 is where things tend to start dropping and stay low. And then a little past 1e-4, now we're spiking up. And I'm not going to worry about this middle part. We're just going to count that as the equivalent of a downward slope. It's not going to be clean. A lot of the times it won't be clean. And some of it's just empirical. Generally what I've found is 1 e neg 3 to 1 e neg 4, 1 e neg 4 to 1 e neg 5 tends to work pretty well if you have trouble, and if if your graph winds up looking like this. In our case, I'm just picking basically between where the rough patches are. So we're going to fit again for 4 cycles and passing in this LR max. So this is the equivalent of the LR choice in our old model, or in the old fastai framework. And as you can see, it does a lot better when we actually pass in a good learning rate, because now we dropped it down to 4%. Now, one thing I'll put here also that I didn't mention is overfitting and underfitting. So right now we are doing what's called overfitting. Our validation loss is lower than our training loss. That's not necessarily a bad thing. It can be. That's where the importance of having some test data that is separate from all of these that you can go and accurately grade your model on, because some overfitting can be good. Maybe it's your validation set just wound up being a little bit easier when you randomly selected like we did. That's okay. It's important to have the other data and the other test set there in order to double back and check our work essentially. So from here, let's continue on down. So we had some different architecture choices. So the ResNet family has essentially 5 different options. You have a ResNet 18, 34, 50, and a 152. Now, what those essentially mean is how deep the model goes, how many layers we're working with. And when we had 34, we had 34 of these what are called res blocks. The deeper you go, the better the model and the better the accuracy can be, but also the more memory it will use. So I wouldn't necessarily run in Colab ResNet 152 with our same batch size and whatnot, because I'll probably run out of memory. So we're going to try with a ResNet 50. Now, I've given you guys some starter code for the data bunch, along with basically a guide to what I want you guys to do and follow. What I want you to do is create a learner again, find your learning rate, fit for another 5 epochs, and unfreeze for 2 more. Now, the only difference between it is when we create our learner, when we create our CNN learner, instead of passing in ResNet 34, we can pass in ResNet 18 and ResNet 50. So that's the important bits that we missed here. Once you're done, I do have the answers down there that you can look at. I believe that was most of the information I wanted to go over with you guys. Now, in the original fastai lectures, Jeremy discusses an image cleaner widget, and there's a new one for the V2 library. However, it doesn't work in Colab still. I tried it out just to see, and it wound up not working. So we'll have to work from there. I may or may not, I'll see if I have time, write a sort of one that will kind of works similar to class confusion that we had back in fastai 1 that I wrote. We'll have to see. Now, the last thing I want to show you guys is the repositories for fastai2. So if we go to github/fastai/fastai2, this is where all the code lives. So the documentation is here at dev.fast.ai. And in it, we can see, let's say I want to go look at the vision core and see what's going on there. I have all this documentation that points back to the source code. And you'll notice that it looks kind of different compared to V1, and that's okay. That's how it should be. especially how the repository looks. So this is built off of notebook.dev, and so everything in the library is built from notebooks. So we have the Python code that lives in this fastai2 folder. So we have like collaborative filtering here, and we can find all of the source code that looks to be, basic Python code. We also have the notebooks, and these notebooks are how you can go and read how everything works in a bit more detail. Like, let's say I wanted to go look at how the visions data works. I'd only recommend this in later lectures after we've sort of gone over in detail, but if you want to go explore, I absolutely encourage it. And so you can see that this is how the library was built. We have this image data bunch here. We can test all the different functions and play around with them, see how everything's working, all right in front of us, and we can debug and try and see what they were working with. Like this right here goes through and checks on the bounding boxes and the tensor images and building from it. And so it's a good way if you want to jump straight in and go explore the code. Jeremy has some wonderful code walkthroughs that kind of walks you through the code base to the point of where you're sort of understanding your way around. They're not for everyone, and that's okay, but I still recommend that you listen to them. And lastly, you have the documentation here, which is just our HTML. A few other things. So Jeremy is starting up the course again. There will be a course V4 starting this spring. If he winds up streaming it, I highly recommend everyone listen. If not, and you're lucky enough to go in person, congratulations. We will definitely be looking at some of his course notebooks and seeing how some things might have changed, some things are different, depending on where we're at and what time we have. The last thing I wanted to go over was how my repository is going to look. So if we go over to a walk with fast or to the practical deep learning for coders 2. So this repository will slowly be updated because I am a college undergraduate. So I'm trying my best to work them out in blocks. Right now I have up through lesson 5. Pets is what we went over in custom today. And next week we'll do MNIST and stochastic gradient descent, along with answering any questions that you guys have that either this didn't answer or that you necessarily might not have gotten an answer to on the forums. So let's go back and check on the forums here because I believe there was a few questions. Yes. Poya7 said, what does it mean if we get widely different plots while running the LR find repeatedly? Running LR find repeatedly can and does give different plots due to the random nature of how the data is selected for the algorithm. Typically, these differences are small. What does it mean when they drastically differ? When they drastically differ, generally, if you're running it repeatedly just to see, my theory on how that works is somehow the weights are still being stored there and they're not necessarily being completely gotten rid of. And so we're slowly trying to fine tune and get a learning rate on something that is already narrowed down from our starting position. And so it's just continuing off of itself. That's one way to think about it. You can check this by completely recreating your CNN learner again, or whatever learner you have, and running LR find as well. You'll find that they tend to be a little bit, not as drastic as a difference, but still a little different. And then would it be possible to show and explain a meaning of a set of LR plots that are more degenerate and are difficult than the ones shown in the classes? So this one's a very easy one to read, but typically what people will experience is something much closer to the one that we had earlier, where it's this. And so I'll just repeat it again. Generally, the threshold is whatever this winds up being where we start increasing, I go about a power below and then 1 to 2 powers below that. And that will be my general threshold to the learning rates I pick. If I have, a graph like this, where we chose 1e neg 6 and 1e neg 4, because they were pretty close to what we wanted to actually have. From here, let me know any other questions that we wound up having, and I will do my best to answer them next week. So, lastly, I'm sorry that we had some tech issues. I'm going to try and get a different room for next week, and hopefully that will help with some of those issues. So thank you guys, and I appreciate all the support, and happy learning.